Sometimes even the computer scientists themselves do not understand how the AI they have created work. How can that be? They know all the code and all the weights, do they not? Yes, they know the basic code and the basic structure of their machines. They know all the weights in their networks. However, any change in the weights has the potential to completely change the whole system, effectively reprogramming it. And sometimes even specific input data can do the same, reprogram the internal logic of the whole network. Only under fixed circumstances, fixed weights and well-known input data, scientists can derive the equivalent computer program capable of performing the same action as the neural network. As soon as any weights change, either through learning or external intervention, it could be a completely new program from now on. Why is that? Well, a bit of theory first. Neural networks are just different kind of programmable computers. They are programmed by changing weights of connections between neurons, also known as parameters. Nevertheless, it is mathematically proven that neural networks can be Turing-complete. What does it mean for a system to be Turing-complete? And how do neural networks meet this criterion? A system is considered Turing-complete if it can simulate any other Turing machine. A Turing machine is a theoretical model of computation that can perform any calculation given enough time and resources. In essence, Turing completeness means that the system can compute anything that any other computer can. Neural networks, particularly those with sufficient complexity, are Turing complete. Universal approximation theorem states that a feed-forward neural network with at least one hidden layer and a sufficient number of neurons can approximate any continuous function to any desired degree of accuracy. This means that, in theory, neural networks can model any function, which is a key aspect of Turing completeness. Recurrent neural networks, RNNs, which include connections that form directed cycles, are particularly relevant here. They have an internal state, memory, that can persist over time, making them capable of simulating Turing machines. Recurrent neural networks can process sequences of arbitrary length and can, in principle, perform any computation that any other computer can, given sufficient time and resources. Thus, neural networks have the theoretical capability to perform any computation that any other computer can. This theoretical property highlights the incredible potential of neural networks in diverse applications, from pattern recognition to complex problem solving. However, there are some important considerations that differentiate neural networks from traditional computers. The most important of them is the inherent plasticity and malleability of neural networks. For example, if you change a program written in traditional programming language even by one bit or one symbol, the program will most probably crash, throw an error, or perform very differently from the original. It is a sad history that one of the first interplanetary cosmic probes lost its way and crashed because a dot was mistakenly replaced by a comma in the original Fortran program. On the other hand, neural networks can be continuously reprogrammed without crashing by gradually changing their weights or parameters. They will work slightly differently, but the changes could be gradual and will not crash the code. That makes neural networks a very convenient tool for learning, reprogramming, and evolving the thinking machines. Evolution can be achieved by applying so-called genetic algorithms, either within a network or among several competing networks. In the realm of computing, we encounter two fundamentally different approaches: explicit and implicit programming. Traditional programming demands that we explicitly write code with clear step-by-step instructions for each task, such as for sorting algorithms. On the other hand, neural networks, through training on data, learn to perform specific tasks, embodying an implicit form of programming. This distinction extends to ease of implementation. Some tasks are naturally suited to explicit programming, while others, particularly those involving pattern recognition and complex data representations, may excel under neural networks. Sure, implementing a complex algorithm using a neural network may require substantial computational resources for both training and execution. In contrast, traditional programs might be more resource efficient for certain tasks. We can say that, in principle, a neural network is equivalent to a program in any other programming language due to the shared property of Turing completeness. However, Any changes in neural network weights, any learning, are to be seen as changes in that equivalent program, effectively reprogramming it. Why can any changes in the weights of a neural network be seen as reprogramming the equivalent computer? In a neural network, weights are crucial parameters that determine how inputs are transformed into outputs. These weights are adjusted during the training process to minimize the error between the predicted and actual outputs. When you train a neural network, you are effectively programming it by adjusting its weights. The training process involves feeding the network with data and using algorithms like backpropagation to update the weights so that the network performs the desired computation. Each change in the weights can be compared to modifying the code in a traditional program. Just as changing a line of code can alter a program's behavior, altering the weights in a neural network changes its behavior and output for given inputs. This process of modifying the weights leads to a new set of behaviors or functionalities analogous to rewriting or refactoring a traditional program. Think of the initial set of weights as the initial version of a program, which might not perform well on its task. Training the neural network is akin to debugging and optimizing the program, with each training iteration improving the weights, similar to how debugging and optimization enhance any program's performance and correctness. Adding new training data or changing the network architecture can be compared to adding new features to a program, requiring substantial modifications to the weights, just as adding features might require substantial code changes. Neural networks can be reprogrammed by simply retraining them with different data or adjusting parameters. They display remarkable flexibility in adapting to new tasks or improving performance. Just like traditional programs, neural networks require maintenance. This might involve periodic retraining with new data to ensure they remain accurate and effective. Diagnosing issues in a neural network can be seen as debugging. Techniques like visualization of weights and activations can help us understand how the network processes data, similar to using debugging tools in programming. Changes in the weights of a neural network are analogous to reprogramming it. The training process adjusts these weights, thereby modifying the network's behavior and functionality, much like how modifying code changes a traditional program. This perspective helps in understanding the dynamic and adaptable nature of neural networks compared to static code in traditional programs. Broadly speaking, the same can be said about specific changes in input data, which can switch a complex network from one state to another, completely changing it. That is the reason why we will not be able to fully understand the behavior of complex neural networks, even if we know the basic algorithms and all the initial weights. Any learning, any new experience can throw the network into new and complex paths of internal consideration. This is similar to how we can know all the basic structure and algorithms of the human neocortex, but still be unable to completely predict the behavior of specific individual. And that behavior will most probably change with each additional learning, any new experience, and even a new internal state. That is the reason why we will never know for sure how our built and trained neural networks really work. Even if by some enormous efforts we would map one specific configuration of our neural network to an equivalent and understandable computer, any changes in weights would immediately result in a completely new computer, potentially quite different from the previous one. And this will happen after any new learning or any new experience by our neural network. This feature makes them even more human, more similar to our own human decision-making process, which is so fundamentally simple if we consider single neurons, yet so profoundly complex if we consider the whole network. Thank you for watching this video. Until the next time, goodbye.